Okay, before we get into looking at specific types of radioactivity, I want to talk to you for a minute about something that was kind of interesting when it was discovered. Remember we said, okay, let's think carbon-14. Okay, so let's suppose we have carbon-14. So that means, and carbon is atomic number is 6. So it means it has 6 protons and it has 8 neutrons. And so if this is the nucleus of carbon-14 with its 6 protons, 2, 3, 4, 5, 6, and its 8 neutrons, 2, 3, 4, 5, 6, 7, 8. And I told you already that the mass of a proton was 1.673 to the negative 27 kilograms, and the mass of a neutron is 1.675 times 10 to the negative 27 kilograms. So we should be able to find out what the mass of this nucleus is, right? Because there's 6 protons, so I can multiply my 1.673 to the negative 27 by 6, and then my 1.675 to the negative 27 by 8, and add them together, and I should be able to get the mass of the nucleus. And that's what we thought would be true. But what we discovered was when we did that, when we multiplied the mass of a single proton by the number of protons in the nucleus and added it to the mass of a neutron times the number of neutrons in the nucleus, the number we got was never actually the same as the mass of the nucleus, like when we actually measured the mass of the nucleus. We always find, not past tense, that the mass of the nucleus is actually less. That somehow when these protons and neutrons go together inside the nucleus, mass goes missing. And this mass that goes missing is called the mass defect. The mass defect. Okay? And it is the difference between the mass of the nucleus and the total mass of the individual protons and neutrons. So it's the difference between the mass of the nucleus and the total mass of the individual protons and neutrons. It will always be negative. Okay, so our equation, and we don't have a nice fancy letter for mass defect. So mass defect is equal to mass of nucleus minus brackets the sum of the masses of the protons plus the sum of the masses of the neutrons. Okay, so add up all the masses of the protons, all the masses of the neutrons, take that away from the mass of the nucleus, and what you get will be negative. The mass of the nucleus will be less, and the negative simply means mass is lost. So the obvious question, good if I could spell lost. The obvious question is, well, where does the mass go? How can mass just be lost, and why? Well, that's where Einstein comes in, actually, and a few other people. But so mass goes missing, but we know mass can't just disappear. What happens is that mass is turned into energy. E equals mc squared energy. So the mass that's missing gets turned into energy, and that energy is used to hold the nucleus together. It's called the binding energy. So the mass defect and the binding energy. Really, they are the same thing, right? You need to think of mass and energy on a continuum, perhaps, right? So mass can be energy, energy can be mass. It can switch back and forth. So the mass that goes missing from these protons and neutrons gets converted into energy to hold the protons and neutrons together inside the nucleus in this tiny little confined space. Okay? Really, we define the binding energy as the energy that we would need to add to the nucleus to break it apart. The energy that we would need to add to the nucleus to break it apart. And that should make sense because it will be equal to the missing mass, so we have to add it in. If we want these protons and neutrons to come out separate, well, then we have to add in energy that's equivalent to the missing mass so they can get their missing mass back before they separate. Okay? So it's the energy needed to be added to the nucleus to break the nucleus apart, and it's equivalent to the mass defect converted into energy. Now, there are two ways that we can convert back and forth between mass defect and binding energy. If our mass defect is in kilograms, then we can use Einstein's E equals mc squared. Put the amount of mass in kilograms in here, multiply it by the speed of light, and the energy we get out will be in joules. But remember that we said that a kilogram is a lot of mass when we're talking about nuclei. And so instead we usually use the atomic mass unit. And 1U is equal to 1.66053886 times 10 to the negative 27 kilograms. So lots of times when we're doing these questions and when you're using this equation, you'll be told the mass of the proton and the neutron in atomic mass units. And so your mass defect will be in atomic mass units. So it's not always, you could then change your atomic mass units back to kilograms using this conversion, and then put that kilograms into your E equals mc squared and get your energy in joules. But just like kilograms, joules is going to be a huge, huge unit. Remember when we were doing photoelectric effect, instead of joules, we used electron volts. Okay? So if we want to switch from kilograms to joules, we would use E equals mc squared. But what if we want to go from and fill in the kilograms, okay? But what if we want to go from binding energy, want to go from atomic mass units to electron volts? So E equals mc squared, but this time the m, we're going to use 1.66053886 times 10 to the negative 27. So we're going to try to find out how much energy is one atomic mass unit. And you're going to multiply that by 2.9979 times 10 to the 8th meters per second. And don't forget to square it. And when you do, you get an energy of 1.492393 times 10 to the negative 10th joules. But we want it in electron volts, so we know to change from joules to electron volts that we're going to divide by 1.602 times 10 to the negative 19 joules per electron volt, just like we always did in the photoelectric effect questions. And when you do this, you get an E of 9.3148 times 10 to the 8th electron volts. And we usually write it as 931.48 mega electron volts. So we say the conversion then is to go, if you know the number of atomic mass units, then to go to figure out the energy, use the conversion 931.48 mega electron volts per atomic mass unit. Okay, so then you don't have to use the E equals mc squared at all. Let me show you in an example, which will run into the next video. So let's suppose in our example that we're going to use the mass of a proton to be 1.007825 U's. and the mass of a neutron to be 1.008665 U's. And when you Google these, you'll find them, like each website